These are examples of what we call linear inequalities in one variable. They're linear because the power, the exponent on the variable is 1. There's only one variable, and they are inequalities. They say that one quantity is less than the other. One quantity is greater than the other. One quantity is greater than or equal to the other. One quantity is less than or equal to the other. That's what we mean by an inequality. We're not saying that two things are equal. We're saying that there's a less than or greater than relationship there. Here we're saying that x plus 2 is greater than or equal to 5. So we're looking for those numbers that if we put them in place of x, it will make this statement true. Well, one number we could put in place of x, we could put 5 in place of x. Because 5 plus 2 would be 7, and it is true that 7 is greater than or equal to 5. I couldn't put 1 in there and make that a true statement, because 1 plus 2 is 3, and 3 is not greater than or equal to 5. 3 is less than 5. But I could put in 4. 4 plus 2 is 6. 6 is greater than or equal to 5. I could put in 3. 3 plus 2 is 5, and 5 is greater than or equal to 5. It happens to be equal to it, so it's either one or the other. It doesn't have to be both. It can be one or the other. So you can see we have a range of values. And wouldn't the very smallest value that makes this statement true be 3? But wouldn't any value greater than 3 make that statement true? So we could say that the solution set to this linear inequality in one variable is all the values of x that are greater than or equal to 3. Well, couldn't I have found that answer by just subtracting 2 from both sides of that linear inequality? That would give me 0. 5 minus 2 is 3. Maybe that gives us a way to solve a linear inequality. Let's take a look at this linear inequality. What values could we put in place of x that would make them less than 7 when we subtract 3? Well, if x was 4, 4 minus 3 is 1. 1 is less than 7. What about if x was 5? Well, 5 minus 3 is 2. 2 is less than 7. How high up could we go? We could go to 9. 9 minus 3 is 6, and 6 is less than 7. Could we go to 7? Or excuse me, could we go to 10? 10 minus 3 would be 7. 7 is less than 7. No, that's not true. 7 is equal to 7. So I can go up to 9. I can't quite go to 10. But I could go to 9.5, couldn't I? 9.5 minus 3 is 6.5, and 6.5 is less than 7. In fact, couldn't I go up to 9.99999999999? I could almost go to 10. I could go to any number that was less than 10, couldn't I? Wouldn't any number less than 10 make that statement true? It would, because we would take that number and subtract 3 from it, and it would be less than 7, wouldn't it? Oh. Couldn't I have found this same statement by adding 3 to both sides of that inequality? Perhaps that gives us a method for solving linear inequalities in one variable. What about this situation? What numbers can we multiply by 2 that will be greater than 8? Well, if I multiply 4 times 2, that's equal to 8, isn't it? We don't want equal, we want greater than 8. So wouldn't it have to be the numbers that are larger than 4? In fact, any number larger than 4, wouldn't 4.1, because 2 times 4.1 would be 8.2, and 8.2 is greater than 8. So any number larger than 4 is going to make that inequality true. Any x greater than 4. Oh, and couldn't I have gotten that by dividing both sides of that inequality by 2? 2x divided by 2 is x, 8 divided by 4, 8 divided by 2 is 4. So perhaps this gives us some plan of attack for solving a linear inequality. And indeed it does. When we solve a linear inequality in one variable, we want to treat it very much like a linear equation, in that we will subtract the same thing from both sides, we'll add the same thing to both sides, we'll divide both sides by the same quantity, we can multiply both sides by the same quantity. There's only one situation we have to be careful of, And that's if we are multiplying or dividing by a negative. Let me show you why we have to be careful of that. This statement is true, isn't it? That 5 is less than 9. What happens if I multiply both sides of that linear inequality by negative 2? Negative 2 times 5 is negative 10. 9 times negative 2 is negative 18. Now, what's the case here? Is this still the inequality that describes this condition? Is negative 10 less than negative 18? No, it's not. Owing $10, you're better off than owing $18. Negative 10 is actually greater than negative 18. What this tells us is, any time while we're trying to solve a linear inequality in one variable, any time while we're trying to solve it, if we have to multiply by a negative number, we can multiply by the negative, but we're going to have to reverse the inequality sign, because that changes the relationship of the quantities when you multiply by a negative. Watch what happens if we divide by a negative. What if we had 14, and 14 is greater than 8, isn't it? Well, what happens if I divide both of those quantities by negative 2? 14 divided by negative 2 is negative 7. 8 divided by negative 2 is negative 4. Now, what's the relationship between these quantities? Is negative 7 still greater than negative 4? No. Negative 7 is less than negative 4. You're worse off if you owe $7 than if you just owe $4. Negative 7 is less than negative 4. So once again, we see that if we have to involve ourselves in dividing by a negative, we do the division and get the answers, but we have to reverse the inequality sign. And so that's going to give us the ground rules for solving linear inequalities in one variable. We will treat them like a linear equation in one variable, but if we ever have to multiply both sides by a negative or divide both sides by a negative, we will be forced to flip the inequality sign after we perform that operation. The next series of videos will have some examples of linear inequalities in one variable and the process we would go through to solve them.